Okay, so now let's talk about time constants. So, what is a time constant? That's the time it takes for a capacitor or inductor to charge up to 63%, or for current to drop down to 37%. Now, where do these numbers come from? Well, let's take a look. So, first, consider the setup. We have an independent voltage source, we have a resistor, we have a capacitor. And I wanted to know the voltage reflected on the capacitor. Okay, no problem. R and C. And then we have V. Now, V out is going to be, well, first, let's consider using KVL. At the time of this, we don't actually know any other method, so we have to kind of deal with using KVL and KCL. So this one for this situation is going to be voltage equals to I times R plus 1 over C integrating from 0 to T, I of tau, d tau. Now, for this situation, it would be better if we talked about it in terms of current or in terms of charge. So this right here reflects charge, and this right here reflects the derivative of charge. And this one's just a constant, so we don't have to worry about it too much. Now, the way we end up solving this, we end up getting the following equation. V of t, which is our V out, is equal to some value times 1. So we're going to just ignore this term for now, and let's say it's something times 1 minus e negative t divided by RC, like that. Now, time constant for this situation, we expressed using tau equals to RC. If you notice, the time constant is just basically when it takes the time it takes for tau to equal to t. Therefore, this is just basically what happens. But if you take a look at this quantity, if we have that situation, we have 1 minus e, which is basically 63%. Similarly, for current, it's going to be something e to the negative t divided by RC. So therefore, if we plug that same expression in, we just get e, which is 30, which gives us roughly about 37%, like that. So that's what we end up getting. Now, what about for inductors? Suppose you have the same setup, but instead of a capacitor, we have an inductor. Well, an inductor, we have to reflect it upon a change in current, like so. Right away, we can find the voltage and current, but I'm going to skip solving this differential equation for now and say, okay, voltage is going to equal to something times 1 minus e to the negative t divided by L over R. And I'm going to put parentheses around here to preface this. Similarly, current is going to be something e negative t divided by L divided by R, just to kind of demonstrate our point. So that means that the time constant in this case is actually L divided by R, not R divided, not LR, but L divided by R. So that's basically the conception behind the time constant. Okay,